Another neat use case for PDG is to speed up actual Houdini setups. And to demonstrate what I mean, let's just quickly build something here by dropping down a sphere, diving in there, setting the sphere to polygon, increasing the sphere's frequency to say 48 like this. Then to this let's attach a null, call this one in, and then on this scatter a few points like maybe 500. And now I want to have these points wander around the surface of my sphere, and I'll for that use a solver in which I'll write a bit of Vex code. So let's dive in here, and in the solver the first thing I want to drop down is a switch which checks if we're on frame 1. So this will switch to the second output if we're past frame 1. So let's write up like this. So once we're playing this back further than frame 1, we will use and work on the previous frame. And if we're initializing this with frame 1, then we'll just use what comes in through the input 1 here. And all I want to do here is just drop down a single point wrangle, which I'll wire up. And in here, I just want to have my points advected with the curl noise. So for that, I'll create 3 vector interface elements, one for the frequency, one for the offset, and one for the amplitude of our curl noise. F for frequency, call this one curl frequency, and let's just copy this one and paste it 2 times. Call one O for offset and another one A for amp. Like this, let's create the interface elements, and we can see they appear here. So let's dial in a frequency of 2, no offset, and a small amplitude for now. Let's dial in 0.02. Next, let's create our curl noise, which will be a vector, call it velocity. And we're going to use the simplex curl noise, which is called curl X noise. Call this with my current points position, multiply it by my frequency, add to that my offset, and multiply the whole thing with the amplitude, your standard noise expression there. Next, I want to move my point position just a tiny bit along this vector. And now what I want to do, if I just let that run and go up, highlight the solver, we see that our points just kind of diverge away from the sphere. So after I move them, I want to project them back onto the sphere. So let's wire in the sphere in the second slot here, then just access the second input slot, wire that in our point wrangle as well. And finally, just project our points position back onto the sphere with the help of the minpause command. We want to project it back on the geometry coming in through the second input slot. That's the one with ID 1 from our current point position like that. And if we dive up again and let this run, we can see now the points stay on the sphere's surface. To that, I'll add a trail, set it to connect as polygons without closing the rows, and maybe having a trail length of 56 frames. So we are generating those streamlines. Let's just quickly highlight the point display here, and for good measure, drop in a resample node, which is just there to generate a uniform spline, and set the length to 0.01 for the individual segments, and we can see we are getting now this uniformly subdivided splines here. And I want to use those spline points to copy spheres on these points. And I want to have those spheres to have a varying scale over the length of the spline. So to do that, in the resample, I'll just check curve U attribute, which will write a U value starting at 0 from the first point and moving to 1 to the end point. And we'll drop down a point wrangle and use that curve U value to generate our P scale for our spheres. So in the point wrangle, let's just set our P-scale to the ramped value of our curve U. Let's call this ramp underscore size, and create the user interface slider like that, and then drop down a copy to points. This goes in here, and a sphere, which we'll set to polygon 2 and maybe have a frequency of 4, and a uniform scale of say 0.1 goes in the other port. Let's highlight that. And you might have noticed that took some time to cook. However, we're now getting those trails here. Maybe the sphere is a bit too big, so let's dial it back to 0.05 like that. And now I want to add a bit of randomness to the individual trails here. And I'm going to do that by multiplying my value here times the random value of our primitive number. So just going to use a primitive number to initialize my random number generator, which then results in these trails here. All right, good for now. Let's merge this with our original sphere coming in through the in slot here. So merge that, resulting in a geometry which looks like this. Now to blend those trails in with the sphere geometry, let's use the old VDB trick, dropping down a VDB from polygons, wire now merge, set our voxel size to a rather small value, 0.005, resulting in this VDB, and then let's just blur it with the VDB smooth SDF, just leaving the default settings here, resulting in something like this, and then convert this back to a mesh, just by using the convert VDB, setting it to polygons. And then when we zoom in, we can see we are getting this mesh here from our VDBs. Sometimes this mesh topology can cause trouble. What we'd like to do here is, for example, use a remesher to generate a bit better edge flow in here by setting the target edge length a bit smaller and letting this run 2 iterations, then wiring this in here. And while this is remeshing, I want to bring up my task manager to show you my CPU load. So let's remesh that. And this is my task manager here. So you can see I've got my Threadripper 12-core processor here, And you can see the CPU is not really used efficiently. We're only having 6% of CPU load in here. That is because I think most of the remesher is still single-threaded. As you can see here, we are just fully using one core. And now we're done. So that actually took some time and didn't even use as many cores as I would have on my CPU. So keep that in mind for later. Let's just finish this with attaching a null and calling this one out_remesh while this is highlighted. All right. Now, if I have a single static mesh and have to sit through the remesh once, that's no problem. I mean, I can just have a coffee or something and let the remesher do its work. However, it gets cumbersome when you have an animation and you have to remesh geometry for each frame, especially when waiting for a single core to finish its work. And that's where we can use PDG to actually leverage the distributed execution of Houdini graphs, even on a single machine, in order to distribute the workload away from the single processor, but run multiple instances for multiple frames of this remesher on different CPU cores. So let's do that. Just heading up, dropping down our topnet, diving in there. And there's very little I have to do in order for all that magic to happen. All I have to do is just drop down a ROP-geo and point its subpath to my out remesh like this. Let's just save this and maybe in the local scheduler increase the maximum CPUs to use to 11. So I still have one CPU left as I have 12 cores on my Threadripper here. So let's save this and cook this one locally on my local machine here, just on my workstation by hitting Shift and V. And again, let me bring up the task manager to watch our CPU load. And there's not much happening because I forgot actually one crucial thing. Let's just cancel this by hitting Shift and D. I want to evaluate not only a single frame, but a frame range ranging from 1 to 240 like this. Again, save this and recook this. Shift and V. So now we are having multiple tasks created here. We're running 11 tasks on the CPU. These are the tasks to go. And this is my CPU load here. So you can see I already get 80% of CPU load with this job, as PDG is taking that single remesher task and distributing it according to what's the status of the current frame. And you might have noticed there are other nodes in there which are not as fast as you sometimes wish them to be, for example, the trail, or I could throw in an attribute transfer here, or maybe a connectivity SOP. So as long as these SOPs get their data in time, PDG can distribute them really, really efficiently and thus speed up the whole calculation of the thing by just using this single ROP geometry node in TOPS. So even if you don't have a farm available and don't want to bother with intricate PDG and top setups, keep this one in mind. If you work in an animation, this can really speed up your whole SOPnet. So while this is cooking, let's just set up the rest of the file. Basically, what this is doing is just caching out our geometry into this files here. So let's just right click on that and go to copy parameter and then head back to our SOPnet here. And after our out remesh, I'm just going to drop down a file SOP, which we're going to use to load back in those files by just right clicking on this file path here and going to paste relative references. So that's going to evaluate, when I mouse click on that, onto our current cache path that we set up in the ROP node in TOPS. So let's highlight that and we can see we are loading back our individual cached animation here. So really simple setup, but one that can speed up a workflow by orders of magnitude. So really powerful setup too.